Hi everyone, thank you for attending the doctoral meetings. I'm Celian Boye, going to present my work in this third year of thesis on the development of and the testing of a magnetic arch thruster, leading by Mario Merino and Giovanni Navarro under the Zarathustra framework project. Very briefly, I'm going to go through the motivation of my thesis and quickly the work that I've been doing during these 3 years. And we'll follow this by the second thruster prototype development, the setup, and the results achieved during the second campaign, which occurred this last month. And I will just briefly go through my work in EP2+, led by also Matteo Guaita, present here. So, Zarathustra, which is revolutionizing advanced H2S plasma thruster for space transportation, is an ERC granted project led by Mario Merino, and I'm in charge of developing and designing the ECR thruster prototype, which is based on a magnetic arch patent, which is a patent Mario has developed. I'm also in charge of making all the characterization experimentally, and I'm doing some simulations with a hybrid code EP2+ developed by the EP2 team to make the simulations on the plasma arch outside of the thruster. During the first years, I've been actually doing a design and realization of a first prototype and also a campaign on this U-shaped prototype. And in the meantime, I was also doing the development of a magnetic field code simulation, magnetic simulation code, as well as a simulation of a microwave expansion in the U-shaped thruster. The campaign and the work that has been done made us improve the thruster to go to the 2ECR thruster, the second prototype, which I've been testing during the second campaign. And in the meantime, as I was saying, I'm doing 2D simulations on the hybrid code. Very briefly, the ECR thruster is the electron cyclotron resonance thruster. We are using a magnetic field and combined with microwaves to generate plasma. As the combination of the two, thanks to the Lorentz force, and also as the fact that the electrons, when they are in a magnetic field, their actual motion transforms into cycloid motions. It combines, and so we have, in the end, thanks to this relation here, the relationship in between the frequency and the magnetic field, and we are transmitting energy to the electrons, which are then creating ions by collision with the neutrals. On the left side, you can see the classic scheme of an ECR thruster, in which we're injecting a power injection, we're injecting a microwave thanks to a microwave guide, an antenna, or a coaxial cable, and then combining this microwave with the magnetic field generated by the coils, we are ionizing the propellant inserted inside the ionization chamber here to create plasma. What about the second prototype we've been developing? On the left part, you can see the prototype itself being assembled during the second campaign, and it's a coaxial ECR thruster, so we are transmitting power to the thruster thanks to a coaxial transmission line. We are using actually this design right here with 2 ECR sources putting one next to another, and the combination of the two makes a closed-line magnetic topology in order also to lower the plume divergence. This is a CAD model of the prototype that you have just seen before. We have actually sorted this in 4 parts. The electromagnets, which are obviously here to produce a magnetic field. They are using up to 1 kilowatt of power to produce 875 Gauss of magnetic field, which is the magnetic field required to enable the ECR phenomena. Regarding the gas filling line, we are using krypton during the second campaign. We should use also xenon, but krypton was the first gas used in order to reduce the cost of the first campaign and to also characterize the thruster. And we have 50 SCCM injection for ignition and 15 SCCM injection for operation. We have an ionization chamber inspired by the work of Onera in Toulouse, and with a length of 50 millimeters and a diameter of 30 millimeters, and to finish with the antenna that you can see right here, which is responsible to transmit the power with a length of 50 millimeters, and we are using a microwave frequency of 2.45 gigahertz in the range of 50 watts to 500 watts, which is the very maximum we can get with our system. During this second campaign, we actually defined 3 main topologies of the 2 ECR thruster. The first one, as you can see on the left, is the magnetic field arch configuration, in which obviously we create this magnetic field arch by having an opposed polarity on the 2 sources. But we also define what we call magnetic field SP, same polarity, configuration in which we are putting the same polarity in both sources, so they kind of repel one another. And we have a third configuration, which is actually a configuration without magnetic field, in the sense that once we have ignited the thruster, we can actually continue to run the thruster without magnetic field, and it would be the last configuration we are using. On the right side of here, you can see this magnetic field arch. It's very subtle, I know, but we have to take better pictures. And you can see the plasma arch forming following this magnetic field line with the closed line geometry. We use the radial polar positioning system in the vacuum chamber, which is in the EP2 lab, with two probes, actually two kinds of probes. First, LPA, retarding potential analyzer, and also two Faraday cups, which are set, as you can see on this scheme. The goal of this campaign was actually to achieve the ignition of a cluster of two ECR sources, which haven't been done before anywhere, and also we wanted to determine the characteristic of the plasma expanding outside of the thruster, and to analyze the efficiencies of the thruster itself. We also want to compare the variability of having two ECR thrusters in a cluster against having just one source, so one simple thruster. Very quickly, because these are just results of the campaign, we have been determining the ion beam energy and also the ion current density to assess the performances of the thruster and the efficiency. It also helps us to understand how spread would be the beam, how good are we ionizing, and how good are we using the mass to determine the performances of the thruster. We can estimate the thrust without direct measurement methods, because we were not using the thrust balance of the EP2 lab in this campaign. Maybe we'll use it in following one. Thanks to these assumptions, and also thanks to the assumptions, we can also compute the efficiencies of the thruster in several configurations. First of all, the thrust lays around 0.2 millinewton for the magnetic field arch, so the closed one, and for the same polarity one. Actually, we have more thrust and more efficiency for the same polarity thruster, which might be due to the closed line geometry of the thruster. And obviously, as you can see, we have quite low efficiency regarding the ionization and the mass utilization. So we have to improve our design and improve our measurements because we see we have an issue, and we are not losing too much energy, which is not used to ionize the gas, and we are using too much mass, let's say, for nothing. However, the divergence efficiency, which helps us understand how spread would be the beam outside of the thruster, is quite high, especially in the same polarity situation, as actually we have quite two focused beams going outside of the thruster. We have also made these measurements and these estimations for the MAT1 thruster, which would be just one source alone. For this case, we are achieving a 0.162 millinewton thrust, and we have a higher efficiency regarding the mass utilization efficiency and the energy efficiency, though we have a more divergent beam coming out of this thruster. Now, coming briefly back to my work on simulations, I'm using the EP2 Plus code developed by the EP2 team, which is a hybrid code, particle in cell, as Enrique just explained, and fluid code to simulate the plasma expansion in 2 dimensions. We are using 3 layers in this code. The main one would be the central one, in which plasma expansion takes place, and the upper and lower ones would be periodic reflection boundaries. And the cell size would be of 2 millimeters. We are, in order to reduce the computation times, we are using a symmetry plane here because, well, we just split the domain in half, so we reduce by half the simulation time and the simulation costs. The goal of this work is obviously to achieve a good understanding of what's happening inside the plasma expansion, but also to compare with Diego's simulations, as in the end is Diego, which will be presenting after me, is developing simulation plasma code in order to assess the plasma expansion outside of the magnetic arc thruster of this double exhaust thruster. So one of the main goals of these simulations would be to make this comparison, and moreover to have a better understanding of what's happening outside of the thruster exhaust. And we are using quantities such as the electron energy, He, to compare the two codes, and moreover the density of ions and also the currents of ions, electrons. In conclusions, during this last year, I've actually ignited the first 2 ECR thruster, the cluster of 2 ECR sources. Also, we have also characterized the one source alone. It was the first ignition for this thruster, and it is yet to be improved by a lot, but I think we have quite some room to make these improvements. Moreover, the work in progress now would be to finish the simulation work and to make the comparison with Diego in order to assess the viability of its code compared to the EP2+1, and also to realize the third prototype and a third campaign with an improved version of the EP2 of the 2 ECR thruster. Also, we have been doing one conference this year, which was my first one in Lisbon for the Plasma Tech. And we will be presenting this work also in the UCAS CEIS conference in Lausanne, in Switzerland, in July. And we plan to release 2 future articles, one upon the simulation and also one upon the characterization of the 2 ECR thruster. Thank you for your attention.